All right, silly people, here's the situation. We have a square of charges around this um, square here with side length A um, with alternating charges on the corners. So I'm going to label this one as Q1. It's going to be minus Q. Q2 is equal to plus Q. I'm going to write them like this. And then Q3 equals minus Q, and then Q4 is equal to plus Q again. And the square is rotating around on its axis with a frequency omega, and then we need to calculate the quadrupole moments as well as the radiation fields in the far zone, as well as the transmitted power. So, I mean, let's just get into it. So, treating the center of the square um, as the origin, you can say that you know the coordinates for all of these guys as being combinations of just a over 2. So this is going to be over 2 with minus a over 2. This is going to be minus on both of them. This is going to be minus plus a over 2, a over 2. And the quadrupole moment is going to be, this is the formula for discrete charges, is qk 3xkij minus r k squared del ij. Right. So first of all, we need to actually, since the square is rotating, we have to get time-dependent forms for where all of these charges actually are. And they'll kind of take this form, where the exposition of a particular particle t at time t, and I'm going to index it particle k. So particle k is going to be the initial position k, or I guess the initial position of particle k times cosine omega t minus the initial y position sine omega t. It's moving in a circle. And then yk of t will be xk of 0 cosine, now this is a sine now actually, sine omega t minus y, or x, no, okay, yeah, this is x, k0, and this is y, k0 cosine omega t, and there's a plus on that. Okay. So from this point forward, I'm going to stop writing omega t and instead write theta, because it's going to be different from the frequency of the propagation of the wave, which I want to denote omega. So this frequency of the square rotating around is now just theta. And this is sine theta. This is xk0 sine theta minus, or plus yk0 cosine theta. Okay. So we can split these up then into x1, x2, x3, and x4, all as functions of t. So x1 of t is equal to a over 2 cosine theta minus a over 2 sine theta. And then y1 of t will be a over 2 sine theta plus a over 2 cosine theta. And through a lot of symmetry arguments, those are really the only equations we need, because the x position of the second particle will be the same as the y position of the first particle at time t. The y position of the second particle will be identical to minus the x position of the first. The x position of the third will be the minus the x position of the first, and then the y position of the third will be minus the y position of the first, and then the x position of the fourth will be minus the y position of the first, and then the y position of the fourth will be minus the x position of the first, or actually positive the x position of the first. All right. So when we calculate our quadrupole moments, we're going to look at the qxx term first. Where was that formula? So sum over k, qk, the stuff. So doing q1, which was minus q, you'll have that it's 3 x1 squared of t minus r1 squared. And then that's going to be plus q, 3, and then for the second particle it was y1 of t. So this is going to be y1 squared of t, and then minus r2 squared. And then we'll have a minus q3. For the third particle we had minus x1, so this is always going to be x1 squared of t, and this is going to be r3 squared plus q, and then you're going to have 3y1 squared of t again minus r4 squared. Okay. And then, so the r's are actually all going to be the same as well, because all of these are just superpositions of the first equation. So rk will be the square root of x, k of t, x k squared of t plus yk squared of t, which are all identical to x1 squared of t plus y1 squared of t. Anyway, so then our quadrupole moment on the xx component is going to be minus 2q 3x1 squared of t minus this thing, and it's squared actually, so x1 squared of t plus y1 squared of t. Okay, and then you're going to have plus 2q, you'll have 3y1 squared of t minus, and then there's supposed to be a minus sign here as well, minus x1 squared of t minus y1 squared of t. And then what's funny is that the r squared terms will all cancel out each other, since all the charges of the particles are the same magnitude. So these will go away, and you'll just end up with, so it's minus 6q x1 squared of t plus 6q y1 squared of t. and then we can write what those are. So we'll have minus 6qa squared over 4. And this is going to be cosine squared theta plus sine squared theta minus 2 cosine theta sine theta. You're going to have plus 6qa squared over 4 cosine squared theta plus sine squared theta plus 2 cosine theta sine theta. It's the squared terms which go away. So this stuff will cancel out here because symmetry. You'll end up with an overall minus sign on the 6 over 4, so it's going to be 6 halves. 6qa squared over 2 times the, actually it's an overall plus sign, cosine theta sine theta, which is going to be 3qa squared sine theta cosine theta. Oh, okay, then you multiply by 2. So you'll get, so there's 2 of these, so you get 6. Yeah, 6qa squared sine theta cosine theta. Sure, I'm not going to calculate what qyy is, because I know from symmetry that it's going to be the same as qxx, but I will calculate the off-diagonal terms now. The first one will be qxy, which is going to be just minus q. You'll have 3x1 of t, y1 of t, and then you have plus q, minus x1, and then positive y1. Those are the x and y positions of those guys. Okay, and then you have minus q. You have an overall minus sign in here, so that's fun. And then you have a plus q, and then again you have an overall minus sign on that. So they all just kind of add up together for a minus 12 q x1 of t, y1 of t, which is going to be minus 12 q a squared over 4. You'll have, you'll just have cosine squared theta plus sine, or minus sine squared theta. Yeah. So it's minus 3q a squared, and then cosine squared theta minus sine squared theta just simplifies to cosine 2 theta. Similarly, the diagonal terms can simplify into just one trig function and end up being 3qa squared sine 2 theta. Okay, you do have to divide by 2 on that one. So that takes care of both the off-diagonal terms. So your total quadrupole moment can be given by this matrix. I didn't do the z components because obviously they're 0. All of these guys are lying on a plane. Z is equal to 0. I'm going to factor out 3qa squared, and then you'll have positive sine 2 theta on the diagonal, then minus cosine 2 theta on off diagonals. And then 0 on any of the z-dependent stuff. So it is traceless and it's a quadrupole moment, and that's looking good. Um, so now we can get our vector potential. Using the quadrupole expansion of the vector potential, you have that AI, that being the I index of the vector potential, will be minus omega squared over 24 pi r e to the I omega r hat and j qij. Yeah, it's just qij. So that's your vector potential. What we can go by this component by component. So setting a to 1, or I to 1, I guess, we have minus omega squared over 24 pi r. We have e to the I omega r. We have x hat, and then we have to sum over j. So x hat times q 1, 1, that is qxx, plus y hat qxy, which is going to be minus omega squared 24 pi r e to the I omega r. You'll have 3q a squared sine 2 theta plus, and that's in the x hat direction, plus 3q, or minus 3q a squared, and that's going to be cosine 2 theta y hat. Okay. Without simplifying further, I'll go on to the next component. That is a2 equals minus omega squared 24 pi r e to the I omega r. Summing over j, we'll have x hat. It's going to be q yx plus y hat q yy. So it's going to be minus omega squared 24 pi r e to the I omega r 3q a squared. That's going to be minus cosine 2 theta plus 3q a squared sine 2 theta. And that's x hat, y hat. Gosh, I wish I was better at writing things. Sine 2 theta, y hat. And so the vector potential will be the addition of these. So a is a1 plus a2. Okay. So you'll need to actually now add these up. And it looks like both of them are just going to be sine 2 theta minus cosine 2 theta with an overall factor of 3qa squared. So we get minus omega squared qa squared 8 pi r e to the I omega r, everything multiplied by sine 2 theta minus cosine 2 theta, and that is in the x hat and y hat direction. At this point, it's worth changing over to spherical coordinates so that we can get the radiation fields. So the combination of x hat and y hat stuff will just give you the roots 2 times r hat. So there's your vector potential. Now you can look at your electric field, and you could use some silly equation that Jackson gave you in this chapter for calculating vector electric fields given quadrupole expansion. Or you can use a Maxwell equation and just say it's minus 1 over t dA dt. And our time-dependent thing is built into theta. So first of all, I'm going to factor through the overall minus sign, get omega squared or qa squared over 8 pi c r e to the I omega r, and then I'll take the derivative with respect to theta of our trig functions. We'll still end up with a root 2 r hat, and then the derivative of theta of 2 theta with respect to time will just be 2 omega naught. That is the actual frequency of the square rotating around. So, that's going to look like omega squared omega naught q a squared over 8 pi c r e to the I omega r. And then that derivative that's just actually omega naught. Yeah, and then that's going to be 2 cosine 2 theta plus 2 sine 2 theta root 2 r hat. So you do get an overall additional factor of 2, which you can just get rid of, move it into the denominator, say it's 4 pi down here, CR, and then you have your propagation piece, you have your root 2, and then you have your superposition of trig functions, like that, and it's in the r hat direction. Now you can calculate the B field at this point, just noting that it's r hat cross E over C, so you will get omega squared omega naught q a squared with a 4 pi c squared r on the bottom with a e to the I omega r. You'll have a root 2, and you'll have cosine 2 theta plus sine 2 theta pointing in the phi hat direction. Okay, and then now you can get towards your angular distribution of radiated power, as always given by r squared over 2 times the magnitude of the pointing vector. I realized while I was editing this that my video feed cut out when I was squaring the E and B fields, so I'm going to do it here. So that's going to be just r squared over 2. We're doing the angular distribution of the radiated power. You're going to have omega fourth, omega naught squared, q squared, a fourth. You'll have your 16 pi squared, c squared, r squared. Your e to the I omega r will go away since we took the complex conjugate of the magnetic field, so that's gone. We end up with 2 there, and then we have the square of this superposition of trig functions. So that's looking like omega fourth, omega naught squared, q squared, a fourth over 16 pi squared, c squared, r squared. The r cancels out actually, so that's good. Then you'll have cosine squared 2 theta plus sine squared 2 theta plus 2 cosine 2 theta sine 2 theta. And then, of course, the stuff inside the parentheses will actually simplify a bit through some trig identities. 16 pi squared c squared. You got 1, and then you got 2. Actually, you don't have 2. You have just the sine of 4 theta. Okay, I think I'm caught up now. Alright, back to the video. And it's going to be literally just 4 theta over t, which is just 4 omega naught. So I can tell you for a fact that the frequency in which the wave is propagating is equal to 4 omega naught. And we can use that to simplify our answer, actually. Okay, and then, so that is just going to be, then omega is equal to 4 omega naught. So you'll have 4 to the 4th omega naught 6th q squared a 4th over, this is 4 squared down here, so pi squared c 4th, and that's 1 plus sine 4 omega naught t. And so you'll end up with a power of 16 on top, with omega squared q squared a 4th over pi squared c 4th, 1 plus sine 4 omega naught t. Okay, then the power will be the integral of that stuff over solid angle. And it doesn't matter how you look at this, whether it's whether you look at omega naught t as theta, or if you just treat it as a constant, then the integral over the solid angle of this stuff just ends up being 4 pi. I checked with various methods. And then 16 times 4 is 64, so you have 64 omega naught 6th q a 4th over pi c 4th. It's really annoying. Be careful, silly people. I actually didn't write q squared at the end there. I meant to write q squared, obviously. Right, and so that's your total radiated power, and your problem is done. Lovely.